We're now going to consider rotational motion. Now, rotational motion, like this, can be a little bit overwhelming because of all the new symbols that are introduced. However, the basic physics underlying it is pretty much the same. So in this video, we're going to look at the analogy between the translational quantities, so that's the movement quantities that you've already seen, displacement, velocity, acceleration, force, those types of things, and the rotational case. And then when we look at rotation in more detail, you'll be able to see how really we're just reproducing pretty much the same equations with the analogous symbol in place. Okay, so first of all, in the translational case, when something moves through space, it has a displacement. In the rotational case, when we have something moving through an angle like this, it has an angular displacement. So we typically use the symbol theta to represent the angular position of the object, and then we can use delta theta to show the change in angle as the object moves. So if this is the initial angle and this is the final angle, then delta theta is just theta f minus theta I, the final angle minus the initial angle. Just as in displacement, we have that the change in displacement is equal to the final displacement minus the initial displacement, and we typically use s or x to represent our displacement. Now, when something's translating, it has a speed or a velocity, which we represent by the letter v, which tells us how quickly the displacement is changing. So we have the equation v is equal to dx dt if we're just considering one dimension in the x direction. We have a completely analogous thing in rotation. So we have an angular speed or an angular velocity, which is given the symbol omega, and omega is equal to d theta dt. When something's moving through space, it can be accelerating, and acceleration is just dv dt, how quickly the velocity is changing, or we can take the second derivative of the displacement, d squared x dt squared, for example. Well, the same thing with rotation. When something's rotating, it can start rotating at a faster and faster pace. I don't think I can turn it faster and faster, but if it's speeding up with time, then it will have an angular acceleration. This is represented by the Greek letter alpha, and alpha is equal to d omega dt, which is equal to the second derivative of theta. So this is d squared theta dt squared. So completely analogous. Now, those ones are fairly straightforward and easy to see. Some of the quantities are a little bit harder to see. So to start something moving, we need to apply a force to it. That's what Newton's first law tells us. An object at rest will remain at rest unless acted upon by an unbalanced force. Now, if we want to get something turning, we need to apply a turning force to it, which is what's known as a torque. So torque is given the symbol tau, and it's analogous to force. Now, Newton's laws all have analogies too. So Newton's first law tells us an object at rest will remain at rest unless acted upon by an unbalanced force. Well, Newton's first law for rotation says an object not rotating will remain not rotating unless acted upon by an unbalanced torque. And we have the similar rules for Newton's second law and Newton's third law. Now, another not so obvious one is mass. So the amount of force will accelerate an object, and the amount of the acceleration will depend upon the mass of that object. Well, in rotational motion, rather than the mass, it's the moment of inertia that is important. So the moment of inertia is given the symbol I, and we'll look at more examples of how to calculate this later, but I is equal to the integral of r squared dm. So what this is telling us for rotation is that it's not just the amount of mass that is important. It's also r, which is the distance from the pivot point, which is important. So if we have a mass further from the pivot point, then it's going to have a greater moment of inertia, and we are going to have to apply more torque in order to get it to move. And finally, in the translational case, we've seen that we have momentum. We've got a similar quantity called angular momentum in the rotational case. So hopefully using these analogies as you work through this topic will show you that really this is just the same thing again, just with slightly different letters. So it may be a good idea to write these down in a table to have next to you as you work through this topic.